That's the second half of Chapter 6, Section 6.2, the binomial probability distribution. This is a longer section. I think it's the longest section we cover in this course, the binomial probability distribution. So the first thing we're going to discuss is what the word binomial means. Then we'll compute probabilities for binomial experiments. We'll talk about the mean and the standard deviation for binomial random variables. We'll see what a histogram looks like, and we'll finally determine if outcomes are usual or unusual for binomial probability distributions. So it's a longer section. All right, so a binomial random variable can only have two outcomes. So again, bi means two, so two outcomes. One of the outcomes is considered desirable or a success, which we usually use an S, and the other is considered undesirable or a failure, which we'll use capital letter F, success or failure. So if we're flipping a coin, we might say that heads is considered a success and tails is considered a failure, or vice versa. If we're rolling a die, we might say that rolling a 1 is considered a success and not rolling a 1 is considered a failure. So it's either a success or a failure. Playing football, making a field goal would be considered a success. Missing would be considered a failure. So it's just one or two outcomes, success or failure. That makes it a binomial random variable. There are 4 specific criteria for a binomial probability experiment. It's on page 310. The first criteria, the experiment is performed a fixed number of times. Each repetition is called a trial. So n, or the sample size, is fixed. I'm going to flip this coin 10 times. I'm going to shoot 10 free throws, whatever it might be. I'm not going to say I'm going to flip the coin until I get a heads and you just keep on flipping, or I'm going to shoot the basketball until I get a shot, and then that would be not fixed. So it's a fixed number of times. No matter how many times you succeed or fail, you're only shooting it or running it a certain number of times. The second condition is that the trials are independent. That means that the outcome of one trial will not affect the outcomes of the other trials. So the trials are independent. Flipping a coin, when I flip the first time, it doesn't matter what that outcome was. It does not affect the success or failure of the next outcome. Same thing with shooting a basketball or rolling a die. Each trial is independent. The third condition, for each trial, there are 2 mutually exclusive disjoint outcomes, success or failure. So there needs to be a clear success or failure. You either make the basket or you miss the basket. You either get heads or you get tails. There's no gray area, there's no confusion. It needs to be very clear, success or failure. And finally, condition 4 kind of goes with condition 2. The probability of success is the same for each trial of the experiment. So the probability of success is the same for each trial. So it's not going to change every single time. We're not going to change anything about the experiment. Each time we run the trial, the probability of success stays the same. Which kind of goes with condition 2. If condition 2 is met, generally condition 4 is met. If condition 2 is not met, then generally condition 4 is not met. So those are the 4 things we're always going to check for to see if they are binomial distributions. So I'm going to look those up. So I have 3 examples, and we need to figure out if these are binomial probability experiments. The first example, an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of shots made is recorded. So the first condition, do we have a fixed number of trials? Yes, we're shooting it 3 times. The second condition, are the trials independent? Yes, and that's just, you just have to think about that. Every time he shoots the basketball, it doesn't matter if he missed or made it the last time. If not, then they're independent. Is there clear success or failure? You either miss or you make it. So a miss would be your failure, and making it would be a success. And finally, is the probability of success the same for each trial? Yes, he has an 80% success rate. So he's going to have to think through those 4 conditions and make sure all 4 are met. The second example, the number of people with blood type O negative based on a random sample of 10 people is recorded. According to the American Red Cross, 7% of people have type O negative blood. So again, the first condition is there a fixed number of trials. We have a simple random sample of 10 people. Again, we're not searching until we find someone with the type O negative. We're stopping at 10, whether they have type O negative or not. So it's a fixed number of trials. The second condition, are the trials independent? The first person's blood type does not depend or change or have anything to do with the other person's blood type, so we can say yes. Is there clear success or failure? I would say yes. You either have type O negative or you have other types of blood. So O negative is considered a success, any other type is considered a failure. And then the fourth condition, is the probability of success the same for each trial? They said 7%. So each time they check, they have a 7% chance of being successful. And then example C, the probability experiment in which 3 cards are drawn from a deck without replacement, and the number of aces is recorded. So the first condition, do we have a fixed number of trials? Yes, we're drawing 3 cards. The second condition, are the trials independent? Now this is kind of tricky. If I have a deck of cards and I take one out and I don't put it back, are the trials independent? No, they are not. Because each time I flip a card over, all the probabilities change. But let's keep going. Is there clear success or failure? Yes, you either have an ace or you don't. So condition 1 is met, condition 2 is not met, condition 3 is met. Ace would be considered a success, not having an ace would be considered a failure. And then condition 4 is the probability the same for each trial. When you do not replace the cards, the answer to that would be no. So again, usually if condition 2 is met, condition 4 is met. If condition 2 is not met, condition 4 is not met. So this is not a binomial experiment. This one is, and this one is. Generally, when you're playing cards and you're not putting the cards back in the deck each time, it is not a binomial experiment. All right. So we have some new notation for binomial probability distributions. We use the letter N for the number of trials of the experiment, which is kind of like sample size. It's about the same. We use letter P to denote the probability of success for each trial. That means that 1 minus P is the probability of failure for each trial. If I have a 15% chance of success, I have an 85% chance of failure. And then we're going to say that X is the number of successes that we want in the trials. X always has to be between 0 and N. We can't want more successes than we have trials. So N is the number of trials. P is the probability of success. And X is what I call the target or desired value. I generally call it the target value. N, P, and X we'll be using a lot for the rest of Chapter 6. So we're going to kind of run this through by hand, and then I'll show how to do this in the calculator. So let's use the example we had previously about the blood types, and we will work this out starting by hand and then using the calculator. So example 2 in the textbook in this section says that according to the American Red Cross, 7% of people in the United States have blood type O negative, just like the other example. A simple random sample of size 4 is obtained, and the number of people with blood type O negative is recorded. We want to construct a probability distribution for this random variable. So we're going to say success, or S, is when you find someone with type O negative blood, and failure, or F, is when we have any other type, or not O negative. So we have success, and we have failure. We have a fixed number of trials. We're only going to sample 4 people. We have a percentage of success for each time, and that stays the same every time we run the sample. So what I'd like you to do, this is going to be kind of a pain. We're going to do this the long way. just to show you what the calculator is doing on its own. So if we have 4 people, the first person, the second, the third, and the fourth, we want to think of how many different ways success and failure can occur. We could have the first person has type O negative, the second person, the third person, and the fourth person all have type O negative. That would be 4 successes. We could have the first person has type O negative, but then no one else does. That would only be 1 success. We could say that the first person was not type O negative, the second person was, and the other 2 were not. That's another way to have 1 success. And I'm just going to continue filling this in of all the different ways this experiment can occur. Some people can kind of see what I'm doing. If not, just kind of fill it in. What I'm doing is thinking of all the different ways to have one person with type O negative. The first person, the second, the third, or the fourth. So there's 4 different ways to have one person with type O negative. We could have the first 2 people with type O negative and the second 2 people don't have it. That would be 2 successes. We could have the first person has it, the second person doesn't, the third person has it, and the fourth person doesn't. That's also 2 successes. We could have failure and then 2 successes and then failure. We could have failure twice and then 2 successes. We could have failure, success, failure, success. And there's one more way. We could have success, failure, failure, success. So what I'm doing is just switching things around as many different ways as possible until I have 2 successes. I don't think I gave myself enough space here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's actually 2 more rows on here. You'll never, ever, ever have to do this. I'm just showing you that it's a real pain in the butt to figure out all the different ways this can happen. So I could have 3 failures and 1 success. Oh, we already did that. Could have 3 successes and 1 failure. Again, I'm just showing you that this is a big pain, which obviously you can see from me working this out. We could have 3 successes and 1 failure. We could have success, failure, and then 2 successes. We could have 2 successes and then a failure. Or we could have failure first and then 3 successes. And finally, we could have no one with type O, all failures. Okay, so there are 16 different possibilities. That got a little messy and it got a little confusing, which it was supposed to be. This is a very tedious, time-consuming, and ineffective method. The only reason I knew that there were 16 outcomes is because I kind of worked it out in my head beforehand. Sometimes there's no way of knowing how many different possible ways. Sometimes it takes a really long time to think of all these different combinations and how many successes there are possible. This is a very tedious, time-consuming, and ineffective way to list out every single possible combination and then count up the number of successes. After you've made this big crazy chart, you would then have to manually calculate each outcome. So all failures, all the different ways to have 1 success, all the different ways to have 2 successes, and it continues and continues. As you can see, this is outrageously ineffective trying to calculate all of these probabilities. We're not going to ever have to do this. I just want to show you how inefficient this is and how frustrating it can be. So we're going to use, the book gives a formula. I don't like the formula either. It's just as confusing as the long way. So the book gives a formula of all the combinations that are possible with their different probabilities. And you can use this formula. The book explains it on page 313. Again, I don't find it helpful. I find it just as confusing. The TI-83s and TI-84s have a function in them that will work this entire formula for you, and that's what I'm going to show you how to do. So moral of the story here is that all of the different by-hand techniques are just confusing and frustrating. So we're going to use a statistical function in the calculator called binomial PDF. We can find this by pressing second bars. So second And then vars is next to the clear button. Vars stands for variables. And we're pushing second vars because we're looking for distributions, DISTR. So if we hit second vars, second vars, you're going to go down, down, down until you see binom PDF, which stands for binomial PDF. And I'll explain what the PDF is versus the CDF. So this can be used for finding exact probabilities for particular values of x. So when your x value is exactly what you want. The first number we put in, so if you push enter, the newer calculators will spell out number of trials, probability, and target value. The old calculators, we have to remember what order they go in. You put the number of trials first, the probability of success, and then the number you're interested in, or your target value. So it's binom PDF NPX. And the newer calculators do this for you. The older ones we have to remember NPX. Number of trials, probability of success, and our target value. So let's use this to fill in. This is from the blood type example. We want the probability of having no success, the probability of having 1 success, 2 successes, 3 successes, or 4 successes. And remember, the probability of success is 0.07, or 7% chance of having blood type O negative. So if I want 0 successes, I have 4 in my sample. I have a 7% chance of success, and I want 0 successes. So 4, 0.07, 0. And that gives me 0.748. I'll round that off to 1. And then I can go to second vars, again down to binomial PDF. I have 4 in my sample. I have a 7% chance of success. And this time I want 1 success. And that gives me 0.2252. You can be a little lazy about it and hit second enter. If you push second enter, it will pull it up again. You can use your arrow key to change the 1 to a 2. So this time I want 2 successes, 0.0254. Second enter, now I want 3 successes. Very small chance of this happening, which there should be because you only have a 7% chance of success. So the probability of having 3 successes should be fairly low. And then the probability of having all 4 successes should be extremely low because you only have a 7% chance of success. So it gives you that e to the -5. That means we have 4 zeros and then the 2, 4, 0, 1, which this is basically no chance. If you're sampling 4 people and you only have a 7% chance of success, it's almost impossible to have all 4 succeed. So it's a very tiny number. If you were to add all these up, we did round, but if you were to add all those up, you should get pretty close to 1.0, which again represents 100% of your distribution. So that's how to get different probabilities. You can use that to fill in a chart or to answer questions using the binomial PDF function instead of using the formula and instead of doing it by hand. So we're going to practice this. Nice and simple. No scenario here, just N, P, and X. I pulled these right out of your textbook. That's why the numbering is kind of weird. It's on page 320 if you want to practice. Compute the probabilities for each one. So the sample size, the probability of success, and the target value. So we're just going to enter them just like that. Second vars, binomial PDF. Sample size is 10, probability of success is 0.4, target value is 3. So binom, I like to write down the calculator function just so that I know where I'm getting my answer. 10, 0.4, and 3, and that gives me 0.21. I'm going to round that off to 5. Yeah, that rounds off to 0.215. The second one, again, binomial PDF. Sample size is 15. Probability of success is 0.85, and I want 12 successes. So second vars, binomial, PDF. I have 15 in my sample, 0.85 probability of success, and target value of 12. And that gives me about 0.2184. So this is about a 21 or 22% chance of this happening. This is about a 21-22% chance of happening. So these numbers we're getting are percentages telling us the likelihood of this particular scenario being true. So this time my sample size is 40. My percentage of success is 0.99, so a pretty good chance of success. And I'm trying to get 38 successes. So the chance of getting 38 successes when you have a 99% chance of success out of 40 tries should be a pretty good number. Let's see. So 40.99, 38. Oh, it's lower than I expected. 0.0532. I was anticipating a much bigger number. Alright, so then the last one, binomial PDF. Sample size is 50, probability of success is 0.02, and I want 3 successes. Binomial PDF. 50 is our sample size, 0.02 is our probability, and we want 3, which is 0.060. I'm going to round that to 7. So 3 or 4 decimal places. The online homework will be very particular about this. Make sure you enter everything correctly. Make sure you round correctly. It has a very small kind of wiggle room on this, so be very careful and make sure to round exactly as they state in the homework, or you're going to be very frustrated. Alright, and I would always recommend writing down what you're putting in the calculator so that you know where these numbers are coming from. So that's using the binomial PDF function to find probabilities of exact target values. We can do the same thing in an actual word problem example. So in this example, 25% of all households are considered wireless only. That means they don't have a landline. Most households nowadays don't have an actual phone connected to the wall. In a random sample of 20 households, what is the probability that only one of them will be wireless only? So this is a binomial PDF. We have a sample of 20. Our percent chance of success is 0.25, and we want exactly 1 to be wireless only. So second vars, binomial PDF, 20, 0.25, and we want 1 to be wireless only. That's 0.0211. So about a 2% chance of that happening. B, we want 5 of them to be wireless only. Binomial PDF. Again, sample size of 20, same chance of success, but this time we want 5 successes. So you can hit second enter and just change the 1 to a 5. That gives us 0.2023, or about a 20% chance of success. And then half of them being wireless only. Now here, when you have 20, half would be 10. We can't put in half. The calculator won't understand what you're doing. So we'll have to do binomial PDF, sample size of 20, 25% chance of success, and you can't put in half. You'll have to put in the actual half of the sample, which would be 10. So binomial PDF, 20, 0.25, and 10. And that is 0.0099. So about a 1% chance of that happening. Again, just be careful entering these in the computer. I know students in the past get really frustrated. Be very careful what you're putting in and make sure you're rounding properly. I would always write down what you're typing in. That way, if you have trouble, you can reevaluate the numbers you're typing in. I will pause there and continue the section in just